So in this lesson, we're going to talk about evaluating limits algebraically. So we're going to use some sort of algebraic manipulation to evaluate our limits. And so to start off, if you look at this expression, x cubed minus 2x squared over x minus 2, we can factor an x squared out of the numerator. But when we do that, we're left with an x squared times an x minus 2 over x minus 2, and if we cancel the common factor, we're left with x squared. Now if you look at the graphs of these expressions, I'll call the first one f of x. F of x equals x cubed minus 2x squared over x minus 2. And then the graph of this simplified version we'll call g of x equals x squared. You see that the graphs are exactly the same except at one point. Right? They don't agree at 2 because our first function has a point of discontinuity at 2. It's not defined there. But we also know that if two functions agree everywhere except one point, then the limits as x approaches that point will be the same, which means that the limit as x approaches 2 of f of x will equal the limit as x approaches 2 of g of x. So, if we want to evaluate the limit as x approaches 2 of x cubed minus 2x squared over x minus 2, well, we could start by simplifying our expression. So we have the limit as x approaches 2 of x cubed minus 2x squared over x minus 2. And if we factor that x squared out of the numerator, we get the limit as x approaches 2 of x squared times x minus 2 over x minus 2. We cancel our common factor, and we're left with the limit as x approaches 2 of x squared, which we can evaluate by direct substitution to just get 4. And so if we look at another example, we have the limit as x approaches 3 of x squared minus 5x plus 6 over x minus 3. We can't evaluate this limit by direct substitution because if we plug in 3, we would be dividing by 0. But I think we can factor the numerator, and it looks like the numerator will factor into x plus 2 times x minus 3 divided by x minus 3. We'll cancel our common factor, and we have the limit as x approaches 3 of x plus 2, which we can evaluate by direct substitution to get 3 plus 2, which is just 5. Now this example looks a little bit different. We have the limit as x approaches 0 of 4 over 7 plus x minus 4 over 7 all over x. And you see again, we can't just plug in 0 because then we would be dividing by 0. But we can do a little bit of algebra to try to simplify things. So in the numerator of our function, we have this 4 over 7 plus x minus 4 over 7. So we can get a common denominator to try to combine those terms. Now it looks like the common denominator in this case would be 7 times 7 plus x. So if we rewrite our limit as x approaches 0, we could multiply that first fraction by 7 over 7, and the second fraction we would have to multiply by 7 plus x over 7 plus x. And this, of course, is all over x. And so now this would give us the limit as x approaches 0 of, so we'd have 4 times 7, and then minus 4 times 7 plus x over 7 times 7 plus x. And now remember, dividing by x, that's like an x over 1. And to divide fractions, we flip the second fraction and multiply. So this is the same thing as multiplying by 1 over x. And so if we simplify a little bit more, we have the limit as x approaches 0. So we would have, that looks like 28 minus 28 minus 4x, because we're distributing. And this is over 7 times 7 plus x times x, because we're multiplying by this 1 over x. And remember, when we multiply fractions, we just multiply straight across. And so I'm going to move to the top here for a little more space. We have the limit as x approaches 0 of negative 4x over 7 times 7 plus x times x. And now I can cancel this common factor of x to get the limit as x approaches 0 of negative 4 over 7 times 7 plus x. And now this we can evaluate by direct substitution to get negative 4 over 7 times 7 plus 0, or just negative 4 over 49. Now, one thing that we might be interested in considering is what happens to our graph as x approaches positive or negative infinity. And so something that you want to have written down in your notes is if you have any positive real number n, then the limit as x goes to infinity of 1 over x to the n will be 0. If I have one thing and I'm dividing it by x to the n, well, as n gets larger, that ratio is just going to get smaller and smaller. And if I have the limit as x goes to negative infinity of 1 over x to the n, that's also going to be 0. And so we're going to use these properties to evaluate limits at infinity. So if we look at this example, we want to find the limit as x approaches infinity of 2x squared plus 3x minus 4 over 6x squared minus 5x plus 7. Well, remember that I can divide the numerator and the denominator by the same thing, right, and not change the problem. So I am going to look at the highest power of x in the denominator, which is a 2. And then I'm going to divide everything by x to that power. So I am going to, really you could think of multiplying the numerator by 1 over x squared and the denominator by 1 over x squared. And so when we do that, every term is going to be divided by x squared. So this will be the limit as x approaches infinity of 2x squared divided by x squared plus 3x over x squared minus 4 over x squared all over 6x squared over x squared minus 5x over x squared plus 7 over x squared. And then I can simplify a little bit. I have the limit as x approaches infinity. Now 2x squared over x squared is just 2. And 3x over x squared would be 3 over x. And then we would have minus 4 over x squared. and this is over 6x squared over x squared is 6. The 5x over x squared would be, oh, that's a minus 5 over x. And then we have plus 7 over x squared. And we're taking the limit as x approaches infinity of all of this. So using our properties of limits, we're really evaluating the limit of each piece separately. And we know that as x goes to infinity, 3 over x will go to 0. 4 over x squared will go to 0. Negative 5 over x will go to 0. And 7 over x squared will go to 0. So really, as x goes to infinity, this ratio starts to look like the fraction 2 over 6, or 1/3. And if we look at another example, in this case, the degree in the denominator is a 4, so we're going to divide everything by x to the 4th power. So we'll have the limit as x approaches infinity of 2x squared over x to the 4th minus 1 over x to the 4th over 3x to the 4th over x to the 4th plus 2 over x to the 4th, which will simplify a little bit to the limit as x approaches infinity of 2 over x squared minus 1 over x to the 4th over 3 plus 2 over x to the 4th. And as x goes to infinity, the 2 over x squared will go to 0. The 1 over x to the 4th will go to 0. And the 2 over x to the 4th will also go to 0. So really, this whole thing is approaching 0 in the numerator and 3 in the denominator, but 0 divided by 3 would still just be 0. And again, if you look at the graph of this function, you see as your x values get larger, your function is approaching the line y equals 0. So also in this section, you may want to evaluate limits of piecewise functions. So remember, piecewise functions are just functions that are defined different ways for different pieces of the domain. So this particular function looks like x minus 3 whenever x is less than 4. It looks like the graph of 1 when x is greater than or equal to 4 but less than 5. And it looks like the graph of x plus 1 whenever x is greater than or equal to 5. So in this problem, we want to find the limit as x approaches 4 of f of x and the limit as x approaches 5 of f of x. And if you look at the picture, right, it's pretty easy to evaluate those limits. But if I didn't have a picture of these functions, I could still evaluate the limit just by looking at our definition for our function. If I start by looking at the limit as x approaches 4 from the left of f of x, then I just check to see what is my function defined to be when x is immediately to the left of 4, and that's x minus 3. So this is the same thing as the limit as x approaches 4 from the left of this x minus 3, which we can evaluate and get 1. And if we look for the limit as x approaches 4 from the right of f of x, then we check to see where x is immediately to the right of 4, what is our function defined to be? And it looks like in this case, it's 1. So we have the limit as x approaches 4 from the right of 1, which of course is just 1. So since the limit as x approaches 4 from the left of f of x and the limit as x approaches 4 from the right of f of x are both equal to 1, then we can say the limit as x approaches 4 of f of x is also equal to 1. And if we want to find the limit as x approaches 5 from the left, well, when x is immediately to the left of 5, it looks like the function is again defined using this middle piece. So we would be finding the limit as x approaches 5 from the left of just the function 1, which of course is just 1, and the limit as x approaches 5 from the right of f of x. Well, when x is immediately to the right of 5, the function is defined to be x plus 1. So this is the limit as x approaches 5 from the right of just x plus 1, which would be 6. And so now you see the limit as x approaches 5 from the left and the limit as x approaches 5 from the right are not the same thing. So that means the limit as x approaches 5 of f of x does not exist.